welcome back to my channel. Today, we're diving into a very important topic for computer science students, the AVL tree. Let's take a look at what we'll cover today. We'll explore what an AVL tree is, delve into rotations, and walk through the insertion and deletion processes. Let's dive into understanding what an AVL tree is. An AVL tree is a type of balanced binary search tree. But what exactly do we mean by balanced? In AVL trees, balanced means that the heights of the left and right subtrees for any node differs by no more than 1. Explain more? Of course. So let's do quick quiz to explain more and visualize it. Take a look at this tree. Is this an AVL tree? If you said yes, you're correct. This is AVL tree. Let's visualize height. The difference in heights between the left and right subtrees is 1 which is equal or less than 1, so this is AVL tree. I'm only showing root node tree difference, but you have to check all subtree for this condition. All subtree. Okay. Now, look at this second tree. Is this an AVL tree? No, it isn't. Let's visualize a height. The height difference between the left and right subtrees is greater than 1, which violates the AVL balance condition. However, we can transform this unbalanced tree into a balanced AVL tree. To achieve this, we need to perform an operation known as a rotation. I will explain rotation in next chapter. In this chapter, we'll dive into rotations used in AVL trees. There are 4 types of rotations: right rotation, left rotation, right-left rotation, and left-right rotation. Don't worry. I'll walk you through examples for each to make sure you understand how they work. Let's start with the right rotation. Remember the last question from our quick quiz in the previous chapter? We make that tree AVL tree with right rotation. Consider an unbalanced subtree where node 46 is the root, with its left subtree having a height of 2 and the right subtree a height of 0. This imbalance is perfect for a right rotation. For a right rotation, we adjust the positions of the nodes. Root node 46 become right node and 40 move up to the root, just like the arrow shows in our diagram. After the rotation, the new root of this subtree is node 40. With this change, the tree now meets the balance criteria of an AVL tree. Let's check another example of a right rotation. This time imagine node 40 has a right child, node 42. The movement of nodes 46, 40, and 30 remains the same. However, node 42 will become the left child of 46 after the rotation, and that's what a right rotation looks like. Left rotation is opposite movement of right rotation. Think of a left rotation as a dance partner swap, but in a very orderly fashion. In the world of AVL trees, left rotation is essentially the mirror image or the reverse of a right rotation. Let's move on to the right-left rotation. Just like it sounds, we start with a right rotation and then swing into a left rotation. Let's break it down with an example. Check out this unbalanced tree. To fix it up, we're going to use a right-left rotation. First step, right rotation. We'll tackle the smaller orange subtree that's tipping things off balance. By applying a right rotation here, we start nudging the tree closer to being balanced. I know it still looks a bit off. Hang tight, I've got this. Second step, left rotation. Okay, so the right rotation helped, but the tree isn't quite there yet. Now, let's hit it with a left rotation on the green tree, which is the current root, to really nail that balance. After these 2 maneuvers, our tree stands tall and perfectly balanced, just like it's supposed to according to the AVL tree rules. And that's how you do a right-left rotation. Pretty cool, right? Alright, now let's move on the left-right rotation. It's pretty similar to what we just covered, but flipped. First, we do a left rotation, and then we follow it up with a right rotation. Let's walk through an example to see how it works. First step. Like I mentioned, we start with a left rotation. We'll do this on the smaller orange subtree. This left rotation helps to get this part of the tree a bit more balanced. Second step. Next up, we apply a right rotation. This time it's on the green tree, which is actually the root of our tree. And just like that, our tree is back in balance, and there you have it. That's how a left-right rotation works. It's a simple 1-2 punch to get everything lined up just right. Alright, let's jump right into insertion. Check out this example of an AVL tree. We're going to insert the number 1 into this tree. Quick recap, remember what an AVL tree is? It's a balanced binary search tree where the left node is smaller than the root, and the root is smaller than the right node. First step. We need to find the right spot for inserting one. It fits right here, doesn't it? So, let's slot it in. This is a crucial step. Now, we have to make sure our tree stays balanced as an AVL tree. If it's not, we'll need to do some tweaking. Look at this, our tree isn't balanced after the insertion, so what do? Yup, we apply a rotation. And there we go, after the rotation, our tree is a happy AVL tree again. Remember, the key to insertion is keeping our tree balanced. And that's how insertion works in AVL trees. Pretty neat, right? Alright, let's jump right into deletion. Take a look at this AVL tree. We're going to delete the number 17 from this tree. First step. We simply remove 17 from the tree. Since 17 doesn't have any children, there's nothing else we need to replace it with. Second step. Just like with insertion, we need to check if the tree is still balanced. Looks like our subtree is a bit off now, so we're going to apply a right rotation to fix it. Now, let's look at another example. Let's go back to our original tree setup. This time, we're deleting 22, which happens to be the root. First step. We remove 22. Now, which number should take the place of 22? Remember, we always take the smallest child from the right subtree to swap in. It turns out, everything's still balanced after this swap, so no rotation needed this time. And that's how deletion works in AVL trees. We remove a node, check for balance, and apply rotations if needed to keep everything perfectly aligned. Thanks so much for watching. Got any questions? Just drop them in the comments below. I'd love to tackle your specific questions and might even make a quick TikTok to explain them, so keep an eye out. And hey, if you liked what you saw, don't forget to hit that subscribe button and give us a thumbs up. Your support really helps. See you in the next video.